Hi, everyone. My name is Chaoran Wang. I'm a PhD student at the University of Michigan. In this video, I will introduce our recent submitted work on the turbulence of ICM. In this work, we will use velocity structure function to describe the property of turbulence. Velocity structure function is the statistical moments of velocity increments. This quantity relates to the power spectrum of turbulent energy. In the classic work done by Kolmogorov in 1940s, Kolmogorov deduced the famous minus 5/3 power spectrum of energy of turbulent energy, as well as the VSF to be proportional to the power to be proportional to the scale to the power of n divided by 3. That's the first order VSF would have a 1/3 slope, as predicted by Kolmogorov theory of turbulence. In this work, we will calculate first order VSF in our simulated ICM and compare it with Kolmogorov's prediction. We simulate the evolution of ICM affected by ICM feedback and cold gas precipitation. And then we measure the first order VSF in both hot gaseous halo and the cold filament structures. We found for both hot and cold phase, the first order VSF have slope larger than 1/3. That means in general, the turbulence in multiphase ICM is non-Kolmogorov. Then we investigate the physical reason that causes this non-Kolmogorov turbulence. In the cold phase, there is more gas flows in than flows out. And also the dominant force affecting the cold gas is gravity. Therefore, the cold filaments rains down to the cluster center. Most of the cold filaments is thus close to freeform motion, where in the freeform motion, the velocity is proportional to the travel distance to the power of 1/2. That's this could lead to the non-Kolmogorov 1/2 slope of cold phase VSF. On the other hand, we found the turbulence of the hot phase is driven by both cold filaments and ICM feedback. Our analysis forms the following arguments that supports the idea that cold filaments stirs the hot gas. First, cold gas mass dominates over the hot phase in the cluster center. Second, velocities are both radially biased in cold and hot phase. Third, the cold and hot gas velocity are spatially correlated. Also, we found after including the magnetic field, the momentum transfer from the ICM jet to the ambient hot gas is facilitated by the magnetic field. Thus, ICM could effectively stir the gas when magnetic field is included. I will leave at the end of this video. I leave the summary of our work here, and it is worth noting that the velocity structure function of ICM can be constrained, that our work can be tested by the future high-resolution X-ray missions.